As we saw, we partition the data either into 3 sets, training, validation, test, or to 2 sets. Both of them are absolutely fine. How do you do that? We're going to use scikit-learn. sklearn is the top-level package for scikit-learn, which is a popular machine learning library in Python. From sklearn.model_selection, we're going to import train_test_split. Model_selection is a submodel within scikit-learn that provides tool for model selection and evaluation, including functions for splitting data sets. Then train_test_split is a specific function within the model_selection module that splits a data set into random train and test subsets. So first of all, we're going to import a CSV file, California housing, and we're going to take a look at the information in our data set. The columns, and then the describe, and then we need some necessary library to import. Import NumPy as NP. Remember that NumPy is a fundamental package for scientific computing in Python. It provides support for large multi-dimensional arrays and matrices, along with collection of mathematical functions to operate on these arrays efficiently. The next one, we're going to import pandas as PD. As you remember, pandas is a powerful data manipulation and analysis library in Python. It provides data structures and functions to work with structured data, such as tables or time series data. And the next library that we need is, we're going to import Seaborn as SNS. Seaborn is a Python visualization library based on Matplotlib. It provides a high-level interface for drawing attractive statistical graphs. And finally, from matplotlib.pyplot, please import matplotlib.pyplot as PLT. So as you remember, matplotlib.pyplot is a collection of functions within the matplotlib library that makes plotting easier in Python. Let's take a look at our data here. I'm in Jupyter Notebook, so please make sure to import pandas as PD and define a data frame. And when you take a look at the columns, let me just run this. You have these columns. All right. You have the price, you have the address, you have the area population, the number of bedrooms. And then when you click on describe, it basically gives you the following information: count, the average, standard deviation, the minimum, first quartile, second quartile, the third quartile, and the maximum. You can take a look at your information and then see what do you have. Now import NumPy as NP, import pandas as PD, import Seaborn as SNS, and import Matplotlib as PLT. Now, From sklearn.model underscore selection, I want you to import train underscore test underscore split. sklearn or scikit-learn is a machine learning library in Python. Train underscore test underscore split is a function from the model underscore selection module in scikit-learn. It is used to split dataset into random train and test subsets. How many subsets you want. Then from sklearn.linear underscore model, I want you to import this linear regression. So we are for now using linear regression for prediction. This imports the linear regression class from the linear underscore model module in scikit-learn. As you remember, linear regression is a machine learning algorithm used for modeling the relationship between one or more independent variables and dependent variable. It also fits a linear model to the training data using the least squares method. Next, I want you to import mean underscore squared underscore error from sklearn.metrics. This line of code imports the mean underscore squared underscore error function from the metrics module in scikit-learn. Mean underscore squared underscore error is a metric used to evaluate the performance of regression model by measuring the average squared difference between the actual values and the predicted values. You also need to import R2 score from sklearn.metrics. This line of code imports the R2 score function from the metrics module in scikit-learn. R2 score calculates the coefficients of determination, which measures the proportion of variance in the dependent variable that is predictable from the independent variable. And mean squared error is 1 over n, the summation of the residuals or the errors yi minus yi hat. Yi is the actual value. Yi hat is the predicted value, and you're going to raise it to the second power. If you don't raise it to the second power and just add these together, you get 0. So let's take a look at one simple example to understand what's going on. There is a relationship between the number of pages in a textbook and its price. The explanatory variable pages can be used to explain some of the deviation from the mean price. In the table below, the number of pages in each book is listed with corresponding price. So X is pages and Y is the price. The number of pages is 560. The price is 119. The number of pages is 579. Price 151.95. X is 606 and price is 122, and so on. So you have X values and Y values. As the number of pages in the book increase, price tend to increase as well. So we can take a look at the data set. Some of them are below the regression line. Some of them are above the regression line. As we talked about this before, when you look at this point, which is associated to 847 in pages with price 182, the difference between the actual price and the predicted price is unexplained. And the difference between the mean and the predicted price is explained variation. So the total deviation of the response variable y from the mean y bar is y minus y bar. The explained deviation of the response variable y from the mean is denoted by y hat minus y bar. The error or the residual is y minus y hat, the actual value minus the predicted value, is the part of the total deviation that is unexplained by explanatory variable x. So the actual value minus the predicted value is unexplained. The proportion of total deviation is in the response variable y that is explained by the explanatory variable x is explained deviation divided by the total deviation. The proportion of total deviation in the response variable y that is unexplained by the explanatory variable x is unexplained deviation divided by the total deviation. So these are the terminology, statistical terminology that you need to know before analyzing the machine learning algorithm, the error function, and how to describe these. Well, the sum of the proportions of total deviation, which are explained and unexplained by x, is equal to 1. So if you take the common denominator and add the explained deviation and unexplained deviation, it is total deviation. So total deviation divided by total deviation is equal to 1. Perfect. Now let us go back to this example. Let us start doing the calculation. X, the number of pages, y is the price, explained deviation is y hat minus y bar. Explained deviation to the second power is y hat minus y bar to the second power. Total deviation is y minus y bar. And total deviation squared is y minus y bar to the second power. For each one of these, we need to do the calculation. 560 and 119. 569, let's go to the second price, and 151.95. So explained deviation for this is going to be negative 18.44. The predicted price minus the average. And then if you raise it to the second power, this is the number that you're getting, 340.0336. And total deviation y minus y bar, which is the actual price minus the average price, 4.35, and it's a positive value. When you raise it to the second power, you get 18.9225. Next set, 606, with price 122, which is negative 14.39. And then you have 207.0721 and the rest. We can basically calculate the explained deviation and total deviation. For each one of these, you're going to do the calculation. What's the point of this? After doing these calculations, we're going to form R squared. The square of the linear correlation coefficient, R squared, is the proportion of total variability that is explained by x when using the line of best fit. This value is also known as the coefficient of determination. Okay. So the coefficient of determination is the explained deviation from the average price divided by the total deviation from the average price. R, as you remember, is always between -1 and 1. So R squared must be a number between 0 and 1. There's a surprising relationship between the proportion of total variability that is explained by the explanatory variable and R, which is the correlation coefficient. We discussed correlation coefficient in previous lectures. Previously, we determined that R is equal to 61.9%. Now, what is R squared? How is R squared related to the proportion of total variation in price that is explained by the number of pages in the statistics book? R squared, you're basically going to just take R and raise it to the second power. It is 38.3%. R squared is equal to the proportion of total variation in price that is explained by the number of pages in the statistic book. So again, R squared, which is 38.3%, is R squared is coefficient of determination, not R. Very good. R is called the correlation coefficient, correct. So R squared, which is in this case 38.3%, equal to the proportion of total variation in price explained by the number of pages in the statistic textbook. So when you see the coefficient of determination in your algorithm, when you are looking at the values that are important in analyzing the algorithm, the performance of algorithm, this is one of them. With a series of individual points like the textbook, we saw that the sum of the explained and unexplained proportions of total deviation was 1. The sum of explained and unexplained proportions of total deviation is also 1. When we use sums of squared deviations to compute the proportions for all points. Now, please note that the proportion of total variability explained by x plus the proportion of total variability unexplained by x is equal to 1. When we use the number of pages to explain the price for a statistic textbook, what percent of total variability is unexplained by least square line or regression line? Well, this is simple calculation. 1 minus R squared is about 61.7%. So the percent of total variability that is unexplained by regression line is 61.7%. What do you think? It can be related to what? We know that 38.3% of variability is related, can be explained by the number of pages. What about the rest of the percentages that you have? What other variables are involved here? Very good. So let's go back to our calculations. What I want you to do, I want you to split the data set into features X and the target variable Y. I want to set X to be California housing underscore, it's just a data frame, and I want you to drop price and address. Why we are doing that? We drop the price and address columns from the features X. Why? The target variable, the price column, represents the target variable that we want to predict. In supervised learning, we train the model to predict this target variable based on the other features in the data set. So it makes sense that we need to get rid of that column for X. We're not using price to make prediction about the price. And then for address, non-numeric data. The address column likely contains non-numeric data, for example, strings. Most machine learning algorithms require numerical inputs. So typically, we get rid of non-numerical data, or eventually we use dummy variables to categorize this. By dropping the price and address column from the features, we ensure that X contains only numerical data set. Perfect. Now, if you want to just have two test and train set, you use X underscore train, X underscore test, comma, Y underscore train, Y underscore test, equal to train underscore test underscore split X, Y, and set test size to be 20% and random state 42. Test size 20%. This specifies the proportion of the dataset to include in the test split. Here's it's set to 20%, meaning that 20% of the data will be used for testing and the remaining 80% will be used for training. So let's go back to our Jupyter notebook. Let me just share this with you. So you have all the information. Let me run it as well. Here we go, everybody. In the next step, we're going to create a regression model and feed it to the training data set. Here we go. Set model to be linear regression and fit the train, X train, and also Y train, both of them, to fit the model. Here we go. Please run the code. And then we want to make predictions on the test set. Set Y underscore pred, which is basically prediction, to be the model dot predict X test. You can also evaluate the model. Is this a good model or not? One of the basic one is using the mean squared error, MSE. Set MSE to be mean underscore squared underscore error using Y test and Y predict. And then print that value for me. What is the mean squared error? What do you have? Seem too big. So that's why we're using different models to see which one is the best model. When it comes to machine learning, deep learning, we are not just using one model to fit the data. So we have different functions to use to measure the accuracy of the model. The popular one is RMSE, root mean squared of error or residuals. And we talked about R squared as well. But let's delve into the basics for RMSE. RMSE is helpful in many areas, particularly in regression analysis or when evaluating models that make numerical predictions. Here are some reasons why it's commonly used. Measure of prediction error. The average difference between the values in the dataset that are anticipated and those that are really present is measured by RMSE. Root mean square of error. This E is referencing yi minus y hat, or the residual. It calculates the difference between the values that are seen and those were predicted by a model. The average squared prediction error is given as a single value using the RMSE formula, which computes the square root of the average squared errors. It is very sensitive to outliers. RSME is susceptible to data outliers. Large mistakes have an excessive negative effect on the total value, since squaring the errors necessitates. In order to recognize and comprehend the effects of extreme forecasts or outliers on the model performance, the sensitivity might be helpful. And finally, it's expressed in the same unit as the predicted variable. This is very important for us. Same units, which makes it easier to interpret and compare across different models or data sets. For example, if you're predicting house prices in dollars, the RMSE will also be in dollars, allowing you to assess the average prediction error in a meaningful and intuitive way. Perfect. What other measures do we have? We have mean absolute error, which is the average absolute difference between the expected and actual values in measure by MAE, is more resistant to outliers since it doesn't punish huge mistakes as harshly as RMSE. Mean absolute error may be preferable if the task requires outlier detection or if you want a measure that weighs all mistakes equally. The next one is mean absolute percentage error. The average percentage difference between the anticipated and actual values is calculated using MAPE. It's helpful when you want to evaluate the model's relative performance across several data scales. In predicting jobs, where percentage mistakes are more important than absolute errors, MAPE is frequently used. R-squared calculates the percentage of dependent variables variation that can be predicted or explained from the independent variables. It may be understood as the proportion of variation explained by the model, and it shows how well the model fits the data. R-squared may be enhanced RMSE by providing details about the model's explanatory power, and it's useful for checking the overall goodness of fit. And finally, F1 score, which is related to precision and recall. These metrics are frequently employed in classification tasks, where the main objective is to predict categorical labels rather than continuous values. Metrics like accuracy, recall, and F1 scores might be more suited than RMSE if your work includes categorizing data into distinct categories or finding abnormalities. So, how do we visualize this? Heat maps visualizing correlation and missing values. Remember, a heat map is a graphical display of numerical data where color is used to denote values. In a data mining context, Heat maps are especially useful for two purposes: for visualizing correlation and for visualizing missing values. In both cases, the information is conveyed in two-dimensional table. A correlation table for p variables has p rows and p columns. A data table contains p columns, p variables, and n rows observation. If the number of rows is huge, then a subset can be used. In both cases, it's much easier and faster to scan the color coding rather than the values. Note that heat maps are useful when examining a large number of values, but they are not a replacement for more precise graphical displays such as bar chart, histogram, and so on. So a heat map, as we saw before, is similar to this. It's color-coded. And as we discussed, the correlation coefficient, darker values denote stronger correlation. Blue, red represent positive, negative values respectively. Now let's go back to our data set. Let's take a look at our code. Here we go. This is the visualization that we did before, looking at our heat map and color gradient in the heat map. So let me share the code with you. You can run this in your Jupyter Notebook or Google Colab. Oh, nice. Somebody's working on AI. Beautiful. So the heat map visually represents the correlation matrix using a color gradient. Positive correlation are typically represented in shades of red, while negative correlations are represented in shades of blue. The intensity of the color corresponds to the strength of the correlation. Stronger correlation are represented by darker shades. And remember that R is bounded between -1 and 1. Look for strong correlations close to 1 or -1. This indicates that change in one variable are associated with predictable changes in another variable. It helps identifying pattern of correlation between different features. For example, in the dataset of housing characteristics, you might expect variable like area, income, and price to have a strong positive correlation. You can also check for multi-collinearity, which occurs when independent variables are highly correlated with each other. This can affect the performance and interoperability of regression models.